Inside a running Kubernetes cluster, the environment is in a constant state of motion. Containers spin up, crash, and relocate in milliseconds, creating a highly chaotic routing environment across your servers. To manage this, Kubernetes splits its architecture into three distinct layers of reality. The foundation is the node network. Think of these as the physical restaurant buildings. They rely on real Ethernet cables, permanent physical locations, and stable LAN IP addresses. Operating inside those buildings is the pod network. These are the workers, the containerized applications. They are entirely ephemeral. A worker process clocks out, a new one clocks in, constantly shifting locations and receiving new, temporary internal IP addresses. If an external request needs to reach a specific worker, it cannot rely on the container's temporary IP. By the time the system memorizes that address, the specific pod may have already crashed and been replaced by a replica on a different server. To bridge the physical infrastructure and ephemeral pods, Kubernetes introduces a third layer, the service network. This acts as a permanent intercom button bolted to the wall. When pressed, the system automatically routes the message to whichever worker is currently active. This diagram maps the three network layers. The node network at the top is tangible infrastructure. The pod network below it consists of actual container interfaces, but the service network is entirely virtual. The service network has no physical cables and no real network interface card. It is an abstraction, a set of rules intercepting traffic and redirecting it to the real destination. Let's trace a single customer request. A user clicks Login on their laptop, sending a data packet across the public internet toward the cluster. The packet first hits an external load balancer. This load balancer knows nothing about internal pods or containers. It monitors the physical servers, selecting a healthy node and forwarding the packet to a specific port on that machine's hardware, like port 30,000. The data arrives at the physical network interface of the server, but before it can reach any application code, it triggers a trap. kube-proxy configures the IP tables. Recognizing port 30,000, it intercepts the packet and executes a DNAT. It checks its list of active containers, selects a local web pod, and rewrites the destination IP from the server's public address to the container's internal address. With the new internal IP attached, the Linux kernel pushes the packet across a virtual bridge and directly into the local web pod's network interface. The external load balancer only gets the traffic to the building's doorstep. From the physical port inward, Kubernetes' internal routing logic takes total control. Now the web pod has the request and needs to verify the user's password. It must query the database. But the database pods are also ephemeral. They scale up, crash, and restart with entirely new IPs. Hard-coding a specific database pod IP into the web application code guarantees a broken connection. The application requires a stable target, a service virtual IP. The web pod discovers this virtual IP by querying the cluster's central directory. The container's system configuration automatically points any unknown host names to this internal registry. That registry is core DNS. The web pod asks for the logical name DB service, and core DNS searches its records and returns the virtual IP, 10.96.0.50. This IP address is a phantom. It is not attached to any physical network card or virtual bridge anywhere in the cluster. The web pod constructs a TCP packet aimed at 10.96.0.50. The moment the packet tries to leave the host node, the local Linux kernel snags the data.
The service VIP acts strictly as a tripwire. Its only function is to catch outgoing traffic and force the local node to make a routing decision. Once the VIP packet is trapped, kube-proxy applies an internal layer of load balancing. It evaluates the available backend pods assigned to that specific database service. It strips away the fake 10.96 virtual IP and replaces it with the actual internal IP of the remote database pod. This creates a critical infrastructure problem. The physical network switch connecting the actual server hardware has zero knowledge of Kubernetes or its internal container IP blocks. If the host machine pushes that packet onto the physical wire as is, the data center switch will read the destination IP, fail to find a valid route, and instantly drop the packet. The cluster requires a specialized translation mechanism to smuggle virtual container traffic across purely physical network hardware. This is where the Container Network Interface, or CNI plugin, takes over.
It intercepts the routed packet and encases it in a new structure. The CNI executes VXLAN encapsulation. It takes the original TCP packet generated by the application and wraps it entirely inside a new UDP envelope. The inner envelope contains the true communication, the source and destination IPs of the pods. The outer header conceals that data, displaying only the physical addresses of Node A and Node B. The encapsulated packet then travels across the physical data center switch. The switch only reads the outer envelope. It sees a standard UDP request from one physical server to another, finds a valid route, and blindly delivers it. Encapsulation is the definitive mechanism that allows a software-defined overlay network to operate invisibly over standard physical infrastructure. The UDP packet arrives at the physical Ethernet port of the destination server. The receiving node's CNI plugin monitors a specific port and intercepts the incoming VXLAN envelope. It executes the decapsulation process. The plugin strips away the outer UDP envelope, discarding the physical IP headers to reveal the inner pod-to-pod packet. The receiving node's kernel reads the true destination IP, pushes the packet across its internal bridge, and delivers it cleanly to the database pod. The database processes the SQL query, constructs the result, and sends it back. The return packet goes through the exact same encapsulation tunnel, arriving back at the web pod to generate the HTML response for the user. End-to-end container communication relies entirely on symmetrical encapsulation and decapsulation to maintain the illusion of a flat network. This flow diagram summarizes the 4 primary Kubernetes binaries that choreograph this network lifecycle. The kubelet acts as the node manager. It builds the environment, writes the DNS configuration files, and requests the container's IP address assignment upon startup. Core DNS functions as the central directory. It translates logical service names into virtual IPs, so pods locate each other without hard-coded addresses. kube-proxy writes host-level IP tables rules, physically trapping those virtual IPs and rewriting them via DNAT. And the CNI plugin wires the virtual interfaces and builds the node-to-node VXLAN encapsulation tunnels to bridge the physical gap. Kubernetes networking relies on a strictly defined, observable chain of DNS lookups, kernel traps, and encapsulation protocols. Once you map the sequence, you can track exactly how the data moves.